Good morning or afternoon, wherever you may be, and welcome to the second Pavement ME User Group Software Training Webinar. I'm Kelly Smith with Applied Pavement Technology, and on behalf of the Federal Highway Administration and the rest of the project team, I'd like to thank you for joining us as we deliver this training presentation, another training presentation on Pavement ME design. The topics for today's webinar are the design of pavements using full depth reclamation and cold in-place recycling, and the design of unbonded concrete overlays of existing flexible pavements. This webinar is being conducted as part of the FHWA contract in support of the Pavement User Group, ME User Group. As many of you know, the User Group project has been led by Jen Albert, Chris Wagner, and Tom Yu at FHWA, with financial support from several agencies that are participating in the TPF 5305 pooled fund. And again, just to clear up any confusion, these user group webinars are separate from the ones being sponsored by AASHTO and the Pavement ME Task Force and conducted by Harold Von Quintus and the other ARA staff. The user group webinars provide additional training opportunities and are designed as extensions of the training that we provide in the user group meetings. The topics for the webinar today were selected from the topic priority list that we developed about a year ago based on input from the TAC member agencies. Dr. Linda Pierce from NCE will provide the training for the first topic, and Dr. Julie Vandenbosch from the University of Pittsburgh will provide the training for the second topic. Each topic is going to be about 60 minutes long, including about 45 minutes of presentation time and 15 minutes of Q&A. And before we get into that, I'd just like to quickly recognize a few folks who've helped us out providing some project information for these demonstrations. And that includes Harry Nair and Brian Diefendorfer at the Virginia DOT, and Chris Brackey and Ben Benami at Iowa DOT. So again, a shout out to those folks who helped us along in developing these training demonstrations. So as we've done in the past webinars, we have some GoToWebinar housekeeping issues that we want to try and get on the table real quick. As usual, Prashant Ram is our man behind the scenes. He's overseeing the GoToWebinar controls, and so we really look forward to him helping us through this, navigate through the GoToWebinar and helping with some of the setting up the poll questions. The process is going to be the same as for the first webinar. So we've got the audio input lines muted and the webinar is being recorded. If you have any questions or comments or other input that you'd like to provide, you can type them in the questions box on the control panel and hit the send button. We will address as many questions as possible at the end of each topic demonstration. And then any questions that go unanswered in the webinar will be addressed and responded to by email in the days following the webinar. We did that in the first webinar and we'll continue that process moving forward. Also, the webinar recording and the PowerPoint presentations will be made available at a later date through an email containing a link to their posting. If you recall, for the last webinar, we provided a link to the pooled fund website, which is where the PowerPoint presentations were posted, and also a link within the pooled fund website for going to the AASHTO ME site where the webinar recording is posted. So that will be the same process as before. With that, I'm going to turn it over now to Linda, who will start the first training topic. Linda. I need you to unmute yourself, Linda.
There we go. Thank you. All right. Do you see my screen yet, Kelly?
We see it. Yep.
All right. Everyone, I'm going to turn off my my webcam just to save me some bandwidth. I'm a little slow these days on that, so I'll be back. All right. What I wanted to do is go through and, as Kelly noted, kind of highlight using the PaveME design procedure to look at cold in place recycling as well as full depth recycling, full depth reclamation. And as we know that just going through the asphalt overlay options, we'll be taking a look at, again, it's the existing asphalt pavement, a flexible as well as the semi-rigid type of process. And I'm not going to get deep into the technology itself, the whole cold in place recycling process, the full depth reclamation process, but at least I want to get some terminology on some of the verbiage that we'll be using a couple different places through the presentation. And so cold in place recycling is certainly just the recycling of the asphalt layers, typically to a depth of 3 to 6 inches. Train comes along, mills up the material, puts it through some type of a pug mill type process, and then lays it down with a paver. The full depth reclamation side, you actually are recycling the asphalt layers and some of the underlying layers, and so you can actually go much deeper. Typical depths now are 8 to 12 inches, and you can kind of see the pattern here. You can see the sheep's foot in the soil there, exposing the pavement layers. So again, much deeper versus the cold in place process. The third one that we'll be throwing around a little bit is going to be the cold central plant recycling, or the CCPR. And this is the classic, do the milling, take the asphalt millings to the plant, go through a processing, do some type of adding materials or adding binder or doing something to that material, and then bringing it back out onto the project site and laying it down with a normal asphalt paver. So those are kind of the three terminologies we'll be using through the presentation. And like I said, I'm not going to get deep dive, but there's certainly a lot of information out there for anybody wanting to know more information on that technology. As Kelly already noted, both Brian Diefendorf and Harry Nair gave us a lot of information. Harry was able to provide us with the DGPX files that he did as part of version 2.2 with PMed, so there'll be a little bit of difference here, and I'll show you that in a minute. We went ahead and also provided us with the Virginia DOT Pavement ME user manual that they developed back in 2017, and then as well as Brian had provided me a report on the I-81 recycling project that we'll be kind of using as our case study in this evaluation process. And then with that, we'll just dive right into the project itself. So it is on Virginia Interstate 81, and it is the southbound lanes only. It's a rural interstate, 4-lane divided, pretty narrow inside shoulders and the typical 8 to 10 foot outside shoulders. And as noted, this is a recycling research project because the Virginia DOT wanted to look into the benefits and practices and performance of all three, FDR, CIR, as well as CCPR. And so this recycling research study was done in 2011. So that gives us some benefit, especially coming on the outside end and being able to compare how PMed actually was able to predict performance, or how does the current performance evaluate or compare to the predicted performance. So, and I got a couple slides on that one to show you as well. All right, so the project location is just is west of Richmond, over in the us on the west coast would pronounce the city as Staunton, but not sure if that's how it is. But so excuse me for anybody on the East Coast. But it's on I-81, running through the just outside the town there, so it's kind of close in, but still pretty rural. And so here's a shot of the typical roadway configuration. So you can see, the asphalt narrow shoulders on the left, pretty standard on the right, divided highway, pretty rural setting. All right, so some of the existing conditions, the pavement itself was about 10 to 11 inches of asphalt sitting on top of about 6.5 inches of an aggregate base. Back in 2011, there was about 13,000 trucks, both two-way, and looking at about 90%, putting about 90% of the trucks in that design lane. Based on the evaluation that the Virginia DOT did, they were having some pretty recurring structural issues with this section of highway. They had a lot of deep patching. They had a lot of mills and inlays, and it was kind of a perpetual. They would fix one, come back and have to fix another section, and so it was kind of this reoccurring issue. And they actually had decided on the project level evaluation that this section of roadway really was a candidate for reconstruction. And that's just some looks at what the distress was, typical distress prior to the rehabilitation. So this is back in 2011. So you can see there's a patch on the left that has a series of potholes in it. You can see quite a bit of fatigue cracking in the patch as well. The image on the right, I was going, hey, wait a minute, that's like a mill and inlay. Now it's actually a patch of a patch type of a thing. And you can see again the fatigue cracking is coming up pretty nicely on the in the right wheel path and actually showing some staining. So we're getting some of the fine material coming up through the subgrade. So you're pretty guaranteed that those fatigue cracks run through the entire depth of the asphalt layer. All right, so just some of the historical pavement condition. Okay, so this is going to be now from a couple, 4 years prior to the overlay project or the rehabilitation project in 2011. And so there's, these increases, pretty much a decrease in IRI. So you're kind of thinking, well, there's something done. And sure enough, those are some areas where there were some potentially localized repairs. So you see the IRI drops in 2008, drops again in 2009, runs back up closer to 225 inches per mile in 2010, and then drops back down in 2011. And so that's where the DOT, even though they didn't have the fully documented information on when these repairs were done, you can kind of take a look at it, that there was no major rehabilitation, but yet IRI was dropping. And on the next two slides, I'll show you that, these potential localized repairs, I'm going to use the same type of a scenario where I show you that those were potentially, they occurred. And one other thing of interest to note too here is on this screen and on the next two slides that I'm going to show, the average value is shown as the circle with the non-filled circle, and then the filled green circles are the maximum in the 10th mile. So it's always nice to look at average alone. We know is not usually the best or the only measure for assessing pavement conditions. So that just kind of gives you an idea that there are some pretty there are higher locations of distress, both on the IRI side as well as I'll show you the rutting and the cracking next. So on the rut depth, again the same thing. Typically, patching and fatigue cracking, you don't solve a rutting problem. And so that's what you can see here is that the rutting still, at least on the maximum values, are increasing, which again, I think the issue was more fatigue related than it was rutting. And even at that, the rutting is pretty low. Even at worst case scenario, it looks like it's only a little bit more than a fourth of an inch. And so it's not anything I think that the DOT was seriously concerned about at this stage. And then finally, looking at patching and cracking, and so this one gets a little bit more messy. But the patching are the circles, and the alligator cracking are the triangles. And again, the marker filled with a color is actually the maximum value, and then the dashed line and the solid green line was the average value. And so again, you can kind of see that for the most part, the alligator cracking on average wasn't terribly bad. Maybe gets up to a couple percent over the years, but certainly the maximum at one location in 2011 was above 10%. A little bit closer, maybe 12, 13%. Then again, the patching, you can see quite a bit of patching happened in 2007. They went through and did some repairs, and that drops and kind of fluctuates a little bit more so, depending on what they did. All right, so let's dive a little bit into the Pavement ME inputs, and this is just looking. Again, this is some of the information that Hari had provided in his version 2.2 analysis of PMed, where looking at also the Virginia DOT identifies the reliability values they use, much like everybody on functional class, where the interstate would be a 95%, and then you can kind of see how it reduces depending on that down to secondary at 80% reliability. They also make a note in their manual that, hey, if you're going to use FDR, go ahead and take a look at the 50% reliability. And so even though I'll show you at 95, I'll also provide that information at 50%, just so you can see how the analysis happens. The other thing is that the Virginia DOT pretty much just takes a look at the bottom-up fatigue cracking and the total pavement permanent deformation as the criteria that they're going. Obviously, they're looking at it all, but they're really kind of focusing on making sure that they meet those two criteria in the analysis process. Now, one thing that we did here, we did have a version 2.3.1, and so even though Hari had done it under version 2.2, the analysis that I'm going to show you is based on version 2.3. If we try to, the 2.2 file format doesn't work in version 2.6, and so Kelly was gracious enough to do all the runs for me because he had an active version 2.3, and so that's what we used through the analysis. All right, so again, as in before, we're going to probably show you more screenshots of software, a little bit more discussion on the results. Hopefully that anybody needing training on how to operate the software itself can go take a look at the AASHTO, where there's a lot of videos there that you can download if you want to know how to run the software. So that's something that we've tended to do previous years, as well as what we're going to do in this session and last one as well. So this is just, again, the standard, and Virginia DOT has vehicle class distribution by project, axles per truck by project, and obviously all the average annual daily truck traffic information is all something that they put in, and then everything else they use a default value. So that was the whole point of showing you that screen. The project location, like I said, is over in the Roanoke area, maybe by that little flag on the screen. This is not from version 2.3.1, but this is a screenshot from version 2.6. Again, just to kind of be able to see where we're at and be able to show you some of the climate summary information, more so than what they show in. Because I think in version 2.3 the map isn't there. I just wanted to maybe show that hey, this is where it's located, just so that we again get a good sense of where we're at. All right. For the analysis of the FDR, there's a couple of different options you could do. You can go in and then design it as a semi-rigid layer, or you can design it as a stiff unbound layer. And so I'm going to go through both of those processes in this next couple of slides. But before we do that, we have a poll question for everybody. And so Prashant or Kelly, if you guys could pull up that poll. And Kelly, I can't see anything.
Oh,
So
I was just going to say, it is being showed, and so people are encouraged to respond to the question shown. Again, just wanted to see what everybody is using in regards to the FDR layer in PMed. So make your voices heard. Prashant, are we getting some good feedback?
Yeah, we are at about 65% response rate, so I'm gonna give it 5 more seconds and then turn it up, and then I'll show the responses.
Great. And can you see it, the results, Linda?
I can.
Okay. I'll let you go through it just a little bit if you want.
Okay, great. Yeah, so thank you everybody, first of all, for responding. It looks like we got about 22% of you say that you do not use full depth reclamation. About 38% model it as a stiff unbound layer, and 28% as a flexible layer, and 12% as other. So that'll be kind of interesting. That's some good information. All right. Thank you, Prashant. Thank you, Kelly. So let's dive into using FDR as a semi-rigid layer. So the pavement section that we're going to evaluate is a 2-inch SMA, 4 inches of a surface mix. Then Virginia put in they recycled 6 inches of the material for the CCPR. So they hauled it off, recycled it, brought it back, and they modeled that though as a asphalt layer, but as a base mix, one of their asphalt base mix layers. There is the recycled 12-inch FDR. Again, we'll model that as a hang on, guys. As an asphalt layer, and then you got to put in a 10 inches of subgrade, because when you get into PMED, it says, hey, you have to have 2 unbound layers in order to be able to run this analysis. And we just took the subgrade, split it, took the top 10 inches, made it into a base layer, and then away we went. So all the properties are the same. And I'll say when Hari went through and did this, he used the 1993 was the original design method, and it was at the time it excluded the 2-inch layer and the 2-inch SMA layer, and they actually came back. The DOT came back and put that on after all the recycling process had been completed during construction. All right, so we're able to just have Virginia send us material properties. And so we do have level 1 material properties for the asphalt, the CCPR layer, as well as the FDR layer. And so this is just kind of to show you those inputs for the binder test and for the dynamic modulus. And you can kind of see the stiffness values there. So I don't, it's good information. If you've got level 1, use level 1 has always been the case that everybody has been supporting. And so we'll go ahead, since we had that data, obviously we're going to use it. Similar on the surface mix layer. Again, we've got pretty good values there for that. 12% binder contact, 6.7% air voids, and then obviously the binder test and the dynamic modulus test results. Then on the CCPR layer, same thing here. Now the effective binder content drops down to 9.8 with the air voids at 6.3, and again still showing a pretty nice. The dynamic modulus itself is still looking pretty relatively good compared to the other two as well. For the FDR layer, it went through and looking at different inputs, and pretty much the DOT uses an elastic resilient modulus of about 7,500 KSI or 750 KSI. And this is again just straight from what Virginia does. But in the ACPA, the PCA, the National Ready Mix, they actually have a little program, pavementdesigner.org is where you can get it. And they actually suggest 600 PSI. And so for anybody not really knowing how to characterize that, certainly the 600 KSI is a good place to start for those values. On the subgrade side, and so again, we had to kind of take off that top 10 inches of the subgrade layer. so we can get the PMed to run, but you can see that everything is exactly the same. Really, it's just 10 inches. Poisson ratio is the same as the subgrade. Stiffness is about 16,000 psi, and then it's an A26 soil. So again, that's just to get the program to run, not necessarily that you're actually building a separate layer. All right, so some of the results, looking at it as a semi-rigid pavement for the FDR, looking at the predicted values, and so these are at 95%. Kind of missing out on the IRI is quite high, but again, if we focus on what the Virginia DOT is looking at, it is the rut depth, and at this pace, it's about twice what they're wanting it to be. But if you look at it at 50%, the rut depth is only 0.26, which it does pass the reliability value at that level. Also, the bottom-up fatigue cracking passes. It's actually quite low. Target is 6, and the predicted values is only 4.3. And then, of course, looking at it, the majority of the total or the asphalt retting is predominantly what's driving the total asphalt retting. So it is all pretty much in the asphalt layers, and very little of it is in the underlying layers. All right. So now looking at it as a stiff unbound layer, and I'll do some comparisons at the end as well. Kind of the similar type of a structure. Again, the 2 inches of the SMA, 4 inches of the asphalt surface mix. The recycled layer is still an asphalt base material. Now we're going to model that 12 inches of FDR as a high modulus unbound aggregate layer, and then it's sitting on top of the A26 subgrade. Won't get into boring you again with the same details, but the SMA material doesn't change. The HMA on the SMA layer doesn't change. The CCPR layer, we're using the same stuff, but now what we're doing on that FDR layer, using a Poisson's ratio of about 0.35, but also saying that we're going to put in a 80,000 psi for its resilient modulus, and then also making it an A1A soil, just to give it a little bit more unbound type of characteristics. But again, it's not probably statistically different between just running it as the regular A2 soil that was before. And the results from that analysis showed that, hey, we're still the predicted IRI actually dropped quite a bit, but certainly the permanent deformation is still failing. It's actually the same as it was for the 95% as it was previously, but at 50% reliability, it's a little higher at 0.36. And certainly the bottom-up fatigue cracking, again, is failing. Even though it's barely failing, it's 6.1 or 6.2% predicted versus the 6% of the target. But certainly at a 50% reliability, it does pass with only 4.3% fatigue cracking. And again, same thing here, that the majority of the predicted permanent deformation is occurring in the asphalt layer, with very little of it happening in the underlying layers. So I don't think that's anything surprising from what we know that happens. So here's this comparison of the analysis. Again, just doing the side by side. With the unbound layer, there is no bottom-up plus reflective cracking, or thermal plus reflective cracking, or fatigue fracture of the cement stabilized layer. So that's why there's a NA in that column. But you can see where I showed before, or said before, that the terminal IRI is different between the two, and certainly it is impacted by the reflective cracking, because you can see that some of that information is coming through. The target was 25 for the FDR as a semi-rigid layer, but actually it predicted 100, and so that was kind of said that, you know, all of the cracking is coming through, being mostly driven by the reflective cracking. All right, and so what the great thing about having this project built in 2011, the PMED analysis obviously was done recently, but we do have measured data. And so Hari was able to send me information related to IRI, rutting, as well as fatigue cracking. And so the benefit, of course, is you can now compare the prediction versus the measured. But also the challenge, as you see here, is trying to figure out, well, what happened, and how well does the measured fit the predicted. And I'm going to show you these. The next 3 slides are all the same in that the measured is lower than the predicted. And there's probably a whole bunch of reasons why that is true. But I think that would probably take a whole nother training session on, on calibration and application of results, and whether or not this needs to have a more forensic type investigation to determine the cause. And so there's a couple. I think there's a couple reasons that there could be this divergence between measured and predicted. But we can dive into that maybe at a later date. So in this graph, again, it's a little bit on the busy side. So the red dashed line at 140 inches per mile is the threshold value they used in the PMED. The light blue lines represent the model if ran as a semi-rigid layer. The dashed line representing the 95%, the solid line representing 50% reliability. And then the black dashed line, black solid line are if you run the analysis with the FDR as an unbound stiff layer. And you can kind of see the difference. And again, it's reflective cracking, I believe, is driving a lot of the problems, or driving the increase in IRI in the semi-rigid analysis versus the unbound analysis. But again, you can see for the most part, the project is riding very smooth. It's still in the 50 range after about 8 years of service. So does that mean it's going to go up and eventually meet the predicted line? Possibly, but certainly it's more time will tell on that one as well. So here's what the rut depth looks like, and the good thing is, since rutting is primarily in the asphalt layers, rutting models used in both the semi-rigid case as well as the unbound case were the same, and so you would expect them to predict the same amount of rutting, and sure enough, it did. So again, I don't think there's any major concerns here on the amount of rutting. As far as between the 2 different models, but again, you can see that the rutting itself is pretty low, and not quite tracking with where it is on the predicted values. For the looking at the bottom up fatigue cracking, and the difference here is on the semi-rigid case. This is considering both bottom up plus reflective, and so again, I think that's obviously what's driving the distress, and it's at the end of the 30-year period, the predicted fatigue bottom up plus reflective cracking in the semi-rigid 50% reliability case is off the charts. It's 200%, which is always fun to have, but you can see it caps off at the 95% reliability. The program obviously caps it off at 100%, which makes a little bit more sense, I guess, mathematically than anything. But again, you can see again the measured are the percent of fatigue cracking, and so it really isn't. There really isn't a reflective cracking portion of that, or it's not distinguished, I should say, because the measure from the pavement management side from Virginia was just about fatigue cracking. So you really can't tell from the surface, obviously, whether it's reflective or not. So this is for the semi-rigid case. For the unbound case, it's slightly different in that the bottom-up cracking is completely related to fatigue. There is no reflection portion of this. And you can see, again, even though the bottom-up cracking is lower, it's still slightly higher. It's higher, twice as high, I guess, where we are today. than what is actually being measured. So again, that's something to look into, I suppose, would be the best to see how that's how come that's not tracking as well as we would hope it to be. All right, so what I did, I also having the ability to run the most current version of PMed, I went ahead and did that this morning, and so this is like hot off the presses, right? So I used version 2.6. I went ahead and said, you know what, I am just going to evaluate one case that's going to be modeling the FDR as a stiff unbound layer. And so this is using the global calibration coefficients. So I should have mentioned that with version 2.2 from Hari, from version 2.3, all the runs that we did, we actually used the Virginia DOT calibration coefficients. So now when you go into version 2.6, those calibration coefficients no longer are the same. And so I just went ahead and said, I'm going to, abandon all the calibration coefficients that we received from Hari. I'm just going to go with the global calibration coefficients for version 2.6. So is it a direct comparison? No, because it's not calibrated to Virginia conditions. But I think it gives us a sense of, so what is the new version? How would the new version look in this analysis? So again, just going version 2.3, then I put both the 50% reliability and 95% reliability for 2.3 and for 2.6, and so you can see that here. Just since there is no reflective cracking in the unbound layer, you don't see that here. And I also only am showing information on the 50% for the 3 criteria that I used on those graphs that I just showed. So just IRI, permanent deformation, and then the bottom-up fatigue cracking. I'm just kind of showing those for reference, since I really don't have a sense of the thermal cracking, the top-down cracking, from any of the results I got from Virginia on the performance of the in situ pavement performance. And so with that, the rutting difference between 2.3 and 2.6 is not, it's not huge. There is a little bit of a difference, but it's nothing. I don't think that there was a big issue or big concerns. Certainly the total permanent deformation in the AC layer, that's a little bit different. It was 0.5 in version 2.3, and now it's 0.4 in version 2.6. And I think based on the calibrations and the model modifications that they made, that probably makes some sense, putting a little bit more deformation in the underlying layers, more so than the asphalt layer. The thermal cracking, interestingly, on version 2.6 is almost 10 times what it was in version 2.3. More likely, the impact of having the climate data files changed from the previous version to where to the mirror values that they're using now. Top-down fatigue cracking actually also reduced from the previous from version 2.3 pretty substantially. So I found that was interesting as well. Now the interesting part too is looking at the bottom-up fatigue cracking, and so we're going back to saying, well, why did they PMEDs over predict or predict a higher, I should say, predicted a higher level of fatigue cracking than what is actually being measured. And well, if you look at the 50% value, or 50% reliability value from version 2.6, it's probably tracking pretty well. So that's also kind of an interesting thing, that taking a look at the difference between 50% reliability and 95% reliability certainly can have that impact on those differences that we were seeing. So I guess just another thing, a food for thought, if anything. All right. Now I'm going to dive into the evaluation of a cold in place recycle project, but I'm going to pause because we do have another poll question for you. So Prashant and Kelly?
And Linda, I was just going to say, we've got only a few more minutes to go on your part of the presentation, but There was a few questions on FDR. Do you want to pause just a little bit and take a couple of those questions, or just wait till the very end?
Yeah, why don't we, Kelly? Why don't we wait to the very end, just so that, because I don't have very many slides on CIR,
Okay.
and that way we can just go from there. And if we don't have time, then I can see if I can't respond to them, and Julie can go ahead, so we don't slow that
Sure.
process down any.
Okay. And it looks like Prashant's got the poll question posted. So if everybody could take a minute to fill in their responses, we appreciate that. I can see that one of the questions that was raised was how long was the project on I-81? And I think I might be able to answer that. I think it was 3 miles. Is that right, Linda?
Yeah, I think officially it was 3.66 miles.
Right.
And the good thing is VDOT did something different in the left lane than they did in the right lane. And it's kind of take a look at that report. And it's actually pretty nicely done.
Yeah. How are we doing on responses, Prashant?
All right, I'm going to close the poll. We have about 65%, and I'll display the results in a moment.
Okay.
Great. Thank you, Prashant. Yeah, it looks like about a even split between CIR is not used and used. You model it as a flexible layer, about 40% for each one of those, and then 12% of you model the model the CIR layer as a stiff unbound layer. Okay, well, thank you for that. All right, and I'll scoot along here, Kelly.
Sure.
All right, so looking at the CIR again, very similar with the pavement structure. So we got a new HMA surface mix. I did a recycled CIR layer, the remaining asphalt. Then there's that 6.5-inch aggregate base. And then certainly as when you model it as an asphalt layer, you got to put in that aggregate layer down below. And rather than going through all the rigmarole of everything, we did do a couple of different comparisons between a 4 or 6-inch SMA layer or a HMA SM layer. We varied the thickness of the recycled, the CIR layer, and so that's why that remaining layer of asphalt kind of goes from 7 to 5 inches, just because depending on how we did everything, what we adjusted for the CIR layer. So there's where that difference is. We do have CIR properties from Virginia, and so we'll just leave that as is and go straight to the results. And so here you can see that as far as IRI goes, it really didn't matter, which again, I didn't expect it to, whether you put in a 4-inch surface mix or a 6-inch, or if you did a 4-inch CIR or a 6-inch CIR. Again, I don't think that's surprising to anybody. The same with the permanent deformation. The rutting is not terrible, even though it doesn't officially pass the reliability check. I would call that good. It's only 0.05 of an inch difference. So in my book, that would be close enough. And you can see the bottom up fatigue is all looking great. Thermal cracking is not an issue. Top down cracking is not an issue. Again, permanent deformation, you do see that again, it's mostly in the asphalt layer. All right. Then if we go and model this as an unbound sandwiched layer. So again, still type of either 4 6 inches on the HMA surface mix. We varied the CIR layer to either be 4 or 6 inches, but we modeled it as 100,000 psi for its resilient modulus. Again, the same remaining, the same aggregate base, everything unchanged in that regard. And here's the results of that. And so looking again, IRI is actually quite a bit higher. Again, it's higher than it was as if you modeled it as a stiff layer. But it's still, it's it's not different depending on what you put in as far as the thickness of the asphalt layer, the thickness of the cold in place recycled layer. Same with the permanent deformation. It's higher, but it doesn't change from one evaluation to the next. The bottom up fatigue cracking is quite a bit higher than it was. It's actually twice of what was in the previous. And again, the total rutting is very again showing that it's mostly in the asphalt layer. One thing that we did find is that other agencies how they model the CIR layer. We were able to find information from both Colorado and Manitoba. Colorado actually did a study looking at field performance. They did a whole bunch of lab testing to quantify the CIR layer. They did a number of PMED runs. Pretty much found out in laboratory testing that the CIR is about half the stiffness of the asphalt dynamic modulus. And they actually suggest that you model CIR as an asphalt layer. Manitoba kind of went through the same process. They actually looked at it both as a stiff layer, as an asphalt layer, excuse me, and as a sandwich layer. But they found that when running the PMED results, it showed that the sandwich layer had unrealistically or unreasonably high overlay thicknesses, where when they ran it as a asphalt layer, it actually came to be a little bit more reasonable as far as the overlay thickness. And so the moral of that story is if you got a CIR, the trend appears to be is to go ahead and model it as an asphalt layer, at least based on the couple of studies that we were able to find, and I'm sure there are others. So this is by any means not a in-depth reference review to come up with that conclusion. So with that, Kelly, I'm done.
Perfect. Thank you, Linda. Very good. We do have some questions, and I think we got one question on the CIR, so maybe we can attack it first. Question is, in the CIR run, the same HMA rutting models and calibration factors were used to predict performance? Question mark. So, any thoughts on that, Linda?
The same.
The same.
Do that again. The same.
Were the same HMA rutting models and calibration factors used to predict performance?
Yes. 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 They were all the same. Yes.
Okay. Perfect. And now let's jump back to some questions on the FDR training. First one was, in order to get 80,000 PSI, was the resilient modulus test run on the FDR material?
I will have to check into that one. I'd have to see. I'll have to see what they did. I'll have to go back to the reports. We'll get back to you on that one.
I know that the Brian and Harry's report, they involved quite a bit of testing on materials, but I'm not sure if that was one of them or not. So I would suspect it is, but like Linda said, we'll get back to everybody on that.
Yeah, I would
Okay.
I would agree with you, Kelly. I would expect it is.
Next question. I'm interested to see if measured stays lower than predicted at year 15. It may be lower now, but once it hits an inflection point, IRI may start to increase relatively quickly.
I would agree. And I think that Kelly maybe is referring to actual. Is that?
Yeah.
Yeah, measured stays lower than predicted. Yeah, no, I agree. I mean, the fun thing about doing these comparisons is it's only been 7 years, and so that's why I was saying don't count it out just yet, because it may change with years. And so I think taking a look at this in another 5 to 6 years would be very interesting.
Good point. Another question, why no AC bottom-up cracking is available when FDR is used as a stiff unbound layer? Why is bottom-up AC cracking not available when FDR is used as a stiff unbound layer?
And let me. There's probably a formal response to that. I don't know that it was modeled originally as part of the original. It's not that it probably doesn't happen, but I don't know that it was modeled that way. Again, we'll check into it.
All right. VDOT limits resilient modulus value to 15,000 PSI for design purposes. For this example, we're using 16,000 PSI. Is this a change from VDOT's manual? A change of 1,000 PSI.
So the value that we used was the values that were provided in the DGPX file. So we didn't change anything from what was from what Harry had analyzed.
Right. Could you explain why the subgrade is separated out as 2 layers again? Explain that purpose of separating the subgrade layers.
I don't know that I can do that without having to go back and reference the document. So we'll have to get back to you on that one.
I think
See, this is why it's important to have Harold, right? Harold, off the top of his head, knows these answers.
Yeah, I think that the main thing there is that you need to have 2, in addition to the subgrade layer, you need to have another unbound layer beneath the bound layers for modeling purposes. So it can be
right, but
go ahead.
I was just going to say, but I'm not sure why that is true. You know, what piece of the calculation forces you to have a two-layer system underneath that layer? That's the question. I think that's the question they're asking, is why does it have to be there?
A deeper dive. That's a good question.
Yes.
Okay. It appears that the effective binder content of the SMA seems a little low, and I kind of noticed that too. I know we got that value from the report that Harry provided, but I'm just thinking maybe that was a percent by weight rather than volume.
Yeah, could be.
And then the last question is, how can they raise the profile by 12 inches? That was the first question presented, but
that we didn't get into, right? Because they went through, and when they did all the recycling, they actually put in 6 inches. So they put 2 inches of the SMA, 2 inches of a surface mix, 2 inches of an intermediate mix. And I believe, you know, that's one thing I never looked. I believe they did go up. I don't know that they took enough of the material and went down, but that would be something I would have to check. So obviously we know that they did a whole bunch of milling, but I just don't know how far down they went.
yeah, and if it's out in a rural environment, they probably didn't run into many vertical constraints, so maybe they could go up that high.
Yeah, and I was when I was looking at the map, there's a major interchange just south of the project, I think it is, or maybe it's just north of the project. So, you know, like I said, it's pretty rural, but you're right. I mean, over a 3.66 mile project, there's probably a couple of interchanges at least. So I'd have to check into that and see what, you know, if they actually removed more material and built it back up versus adding. That's one thing I did not check into.
Okay. And Aladdin has voices information on the subgrade separation. So he says the model is developed based on 2 unbound layers. And I totally agree with that, but I think, like Linda said, we probably need to dig into that a little bit further, why that was specifically set that way.
Right.
And another comment, if the subgrade has a higher moisture content, is it still a candidate for FDR?
And I will defer that to the experts for FDR. It's not something like I said at the beginning. We're not going to go into the differences of the treatments, but I would certainly refer you to one of the websites that actually does do the FDR. Unless there's somebody on the call right now or online now that would have a quick response to that answer, that would be appreciated as well. Otherwise, we'll have to get back to you.
And let's maybe catch one more question, and then we'll let Julie get going with her presentation. The question was, should the FDR stabilized with asphalt be modeled as flexible and FDR with Portland cement as semi-rigid?
You know, I don't know that the model within PMed is sensitive enough to flexible versus cement, because it's all about properties, stiffness, dynamic modulus, and so I'm not sure it would make it. I'm not sure it makes a. I don't know that it's a significant enough difference to impact the results, but that would be something certainly to check into. But
yeah, it's kind of a logical thought process, but like you said, I think it's maybe not sensitive to that as one might think.
yeah, because you know the fun thing to remember is that the FDR model or the process has not been calibrated. So I wouldn't, at least at this point in time, I would say it doesn't matter. It doesn't matter just because it's got an uncalibrated model. However, if you're, you know, have enough of the information to have both an FDR with asphalt and FDR with cement, and to be able to generate a difference, obviously that would be the ideal way. But I don't think the way it is today, I don't think it would. Obviously, since it's not a calibrated model, it wouldn't be something that I would suggest.
All right. Well, let's. We will. There's a few other questions here, but we're gonna move on. We'll let Julie get going on her training for the PCC overlays. And again, like we've said before, we will address all these questions and comments, and we will put a complete list of responses together and put that out to all participants. So Prashant, can we move on to Julie now? Looks good, Julie.
Okay, great. Thank you, Prashanti and Kelly. So yep, I guess I follow up Linda here, and we'll be presenting on conventional white topping. Originally, this was advertised as kind of an expanded version with conventional white topping and unbonded, but because of the volume of the content, it was almost too much to put in one presentation, so we just opted to go and focus on the conventional white topping and then jump back to unbonded at a later date, and also bonded concrete as well. So with that, I'd like to acknowledge Chris Brakey and Ben Benami with the Iowa DOT, because of course, if you're going to be talking about conventional white topping, then Iowa's going to come up, and they were kind enough to provide us with some project information. So again, here we are with our overlay design options, and we're going to be looking at specifically distressed asphalt pavements, and that's where our focus will be. Just to get some terminology correct and get our mind straight on where we're at, again, we're looking at a distressed asphalt pavement where we're going to put a jointed plate concrete pavement on top, or possibly a composite pavement, and I'll just briefly talk about that in a second. But with the distressed asphalt pavement, it seems like there's a lot of confusion, and I frequently get questions with respect to what's the difference between bonded and unbonded, and does it really matter? And when you're selecting a design process, there are some things that you'd like to consider. So which approach do I take? And it looks like I'm not able to forward my slide. Now it's going. So which approach do I take, and what design alternative should I focus on? And how do I make that decision? Well, it's going to be a function of the overlay thickness. And of course, you know, as soon as you say, well, if it's going to be a function of the overlay thickness, how can I design the pavement. I wouldn't need to develop a design if I knew what the overlay thickness was, already. And just remember that just like with the 93 design guide, thickness design is an iterative process. So for example, if you're going way back to calculating a K value, well, you need to know the thickness of the slab prior to calculating the K value. Or even if you're going back to easels, then you also need to know the thickness of the slab. So you give a best estimate of what the thickness is, and then you try the design, and then you move forward from there. And it's somewhat similar to this process. And even in the design example, I'll show you how it works. So with the overlay thickness, the critical value is 6 inches, and that's sort of the turn point. And when I'm doing a design and it comes out to about 6 inches, I'll design it both as a conventional white topping or conventional concrete overlay unbonded, and I'll also use the bonded methodology just to see where that gets me. So with the 6 inch, if we're 6 inches or less, again, that's the bonded concrete overlay. The design tools, then you can use the BCOA if you're looking at all slab sizes. So the very small 4x4 or less, the trendy 6x6, or even full lane width slabs, for example, 12x10 or 12x12. If you're going to do the short slabs, then of course you have the Pavement ME that you can then use with the short slab design option, or the Colorado design procedure, which was really the crux of the foundation of which the BCOA ME was designed on. And then if it's very small slabs where you have corner breaks as your primary mode of distress, then you can use the ACPA design procedure. So all of that we had talked about in a previous webinar, but our focus on this webinar is when your thickness is at or greater than 6 inches, and you're going to be developing a conventional concrete over asphalt design. So in doing that, you have two options. You can use Pavement ME, and of course, we've been using the 93 guide for quite some time. In the 93 guide, you're just designing a concrete pavement as if it was a new pavement on top of an asphalt base, much of which we're currently doing in Pavement ME, but there's some things that Pavement ME can account for the existing conditions a little bit better than what we had in the 93 guide. So that's kind of our focus. I also wanted to mention distressed composite pavements. We had talked about this a little bit in previous webinars, but you have the same type of thing. But now instead of looking at this as an unbonded overlay, or should it be a bonded overlay, or should it be just a conventional asphalt overlay, how do we design this? And again, you have to ask yourself, first of all, this time you're going to ask yourself, how thick is the asphalt? And 3 inches is kind of your intermediate area, which you're probably going to go both ways, because typically if you're going to have an asphalt interlayer, so a composite pavement, you're going to mill the asphalt down to the thickness of the interlayer, and then you'll have like maybe 1 to 2 inches. Some people leave up to 3. You get much more than that, and it's going to be responding a little bit differently. So if it's less than 3 inches, then that's going to create a slip plane, and you're going to design it as an unbonded. And we'll talk a little bit more about that in a future webinar. So here's some of the design tools, of course, Pavement ME, and then the Pit UBOL ME, which has some different advantages, and then of course the 93 guide. But if we're on the other side of that and it's greater than 3 inches, then that can be designed as a white topping, because that layer is going to act not as a slip plane, but it'll contribute in carrying the load. So then again, do we go to a conventional design, or do we design this as a bonded concrete overlay? So that's when we go back to the overlay thickness. If the overlay thickness again is going to be 6 inches or greater, we'll treat it a little bit differently. So when it's thinner and we're going to engage that asphalt and it's going to carry the load together, then that's when we're going to use the conventional bonded concrete overlay tools that we had just talked about. But then if it's greater than 6 inches, then you're going to go to the Pavement ME Or again, if you're using the 93 guide, it's a new pavement on top of an asphalt base. So it's pretty straightforward in how you kind of climb down to what design tool you should use, but you want to have a little bit of an estimate of where you're going. And again, you know, that's the whole idea of the design process. If it ends up being a little bit thicker than you anticipate, then you might want to go over and design it more as a conventional, where if it's a little bit thinner, you might want to double check to see what it would come out if you have a bonded concrete overlay. So I think we're ready for the poll question number 3, Kurt, if that's all ready to fire up.
And Prashant's working it. There we go. You probably can't see it, Julie, but it is being shared right now. So we
Okay.
ask everybody to go ahead and participate in the poll question. And I guess we could even, you know, this doesn't need to be geared towards state agencies or provincial highway agencies. This could be local agencies, but even personal driveways, folks that have their own driveway and are wanting to do a white topping on it, feel free to respond to this poll. And how are we looking on response rates, Prashant?
Almost 60% here. I'm going to turn it off in a couple of seconds and show the results.
And I hope I haven't biased it by saying that part about the driveways, because now we're going to have a bunch of zeros. And the results are being shown. Can you see them, Julie?
I can't seem to see the results here.
Okay, I'll just go ahead and relay the information. So we have 56% said 0 projects are built in a year, 38% at 1 to 5, and 5% at 6 to 10, and 1% at more than 15. So not a whole lot of usage out there, but that's kind of what we're seeing based upon these responses.
Okay, great. Well, maybe this webinar will help provide some more information to this area, and people will have the information they feel comfortable with to do this type of design. I think the next is for poll question number 4, Kurt, if you would like to proceed with poll question number 4.
And he's got it posted, and this is on the design procedure for conventional white toppings. So some different options there for folks to weigh in on. And have we hit the magical 67%, Prashant?
Well, not yet. We're close to 50%. I'm just going to give it a few more seconds to see if folks want to respond.
All right.
Yeah, we are over 50%, and I'm going to turn it off in a couple of seconds.
Okay, and we have some results. So it looks like 22% are using PMED for conventional white topping design, 32% using AASHTO 93, and we do have 20% that are using both. So using both procedures and probably interpreting what the best design might be. And then we have 26% who say other procedures. All right, those are poll questions 3 and 4. Back to you, Julie.
All right, thanks. And you know what? I actually like the fact that people are using multiple tools because they're all based on different conditions, and it's good to kind of get an idea from different perspectives, different design processes on what the thicknesses should be. So I'm going to now focus back on conventional white topping or concrete over asphalt. So with the concrete over asphalt, again, this conventional white topping, it's thicker, and we're not relying on that bond. And so, you know, the design philosophy is a little bit different. So with this, I first want to talk a little bit about what the assumptions are within each design process. So with this type of a structure, you can design it as an overlay on top of a jointed plain concrete pavement over asphalt. The same type of design process, again, is used for the short joint. And then also a similar process is used when you're using a new design in concrete over asphalt. So if I look at these 3 different alternatives, then what assumptions are inherent with each? And the big thing, as we had talked about before, with the slab thickness is if you're going to be having a thicker slab, then that's more of a new an overlay that you would design a jointed plain concrete over asphalt. So in the overlay option, you go to the jointed plain concrete pavement and then over an asphalt. So within the short joint, you're assuming that's kind of a 4 to 8 inch range. That's the window, and I would even venture to say 8 inches, probably a little bit outside of the inference space a bit based on the calibration database. But when you're looking at slab length, that's going to be a differentiating factor as well. For your short joints, that's 5 to 8. For the new design, that's 12 to 20. Again, I think it will go down to 10, but you're outside your inference space. You'll get a bit of a warning too, I believe, if you enter 10 feet. So 10 to 20, and of course that 20 portion is quite long for a conventional white topping or a concrete overlay on top of asphalt. So then when you get into the asphalt stiffness, that's where we start differentiating between these 3 design options within Pavement ME. So for the short joint spacing, what you're doing is you're adjusting the asphalt stiffness based on the assumption that there's 65% fatigue cracking that has developed. So that's quite large. But that was more of a calibration factor that they used, and that's how that was established. So that's a constant. Regardless of the distress in the asphalt pavement, you are correcting the asphalt stiffness based on the assumption that there's 65% fatigue cracking. Okay, so with the overlay option where you're doing a jointed plain concrete pavement over asphalt, as you'll see in a few minutes, what you're doing is reducing the stiffness of that asphalt as a function of the percent fatigue cracking. And you'll find that as you go pretty much lower and start getting more distress, it can have a significant effect on the thickness of the overlay. And this is what we do in the BCUA ME as well, but with that, of course, you're relying on the bond, so you want the asphalt to be in relatively good condition. And so within those lower percents, so the upper quality, the lower percent fatigue cracking being present, it's not as sensitive as you'll see as it is here for a conventional white topping. Now, when we use the new design and you design a concrete overlay over an AC base, how does that differ from the overlay design? it's pretty much exactly the same, with the exception that you're getting new asphalt, and the reduction of the stiffness of the asphalt base isn't accounted for because it's obviously a new base layer. So what's primarily the difference between a new design of a jointed plate concrete pavement on top of an asphalt base and an overlay design of a jointed plate concrete pavement over a distressed asphalt layer is the reduction in stiffness of the asphalt layer that you get when you have fatigue cracking present. And that accounts, you know, if you look at how the structural model is, which is just the model used to calculate the stresses and strains which relate to distress, it considers these two layers as one slab. So that it just looks at one slab, but the composite stiffness of all these layers. And it does that uniformly across these different design options. So the other thing that's important that differentiates these is that the calibration database used for the JPCP over AC, the overlay option, that's based on data for new pavements, where the short jointed is more based on a BCOA. So the calibration databases are more similar for the new design and the overlay design, but again, the big difference is how you account for the stiffness of that asphalt layer. And sometimes this forward is sticking. So, okay, so here we are now. Then I want to go through the pavement ME design process and look at specific things that are associated or affiliated just with this type of design, just with this concrete overlay over asphalt design. And so, you know, there's obviously a lot of different inputs that we use, but you know, traffic's the same throughout our designs, and you know, a lot of these other components, climate, it's all same throughout the other designs. But I'm going to just focus on the specific design options within the concrete overlay over asphalt. So the first thing that you come to when you're doing your design is looking at the layer properties for your overlay. And the big thing with this is selecting the erodibility index based on the layer that will be pumped. So I think it's important to remember that the material that's being pumped for a white topping is going to be pretty much always the material below the asphalt layer. So when we're looking at what's being pumped, and if you just assume it's directly the layer below the concrete, that's not probably quite true when you have a concrete overlay over asphalt, because as those joints open up, that crack propagates down through the concrete and through the asphalt as well. So that joint activates typically through the concrete and the asphalt layer. So a lot of times the material you're eroding is that base layer. And if you look at some of the LTPP data, it supports this, where we have different concrete pavements on asphalt stabilized bases, and the erodibility of the layer below the asphalt layer does play a critical role in the development of faulting. So I think that's one important thing to see. The other thing is that we have to define the friction for the pavement structure. And as we had mentioned, you know, through this conventional pavement, we're not really relying on the bond between the asphalt and the concrete, although it will be there because it's very easy to bond these two layers together. I'm sure that Chris and Ben will testify to that. Concrete bonds very well to asphalt, milled or not milled. So the other thing is what's considered to give you a good prediction. And the manual of practice recommends that you assume full friction between these two layers throughout the life of the pavement. So unless you have strong evidence otherwise, I would follow the manual of practice and assume full friction between these layers. Okay, so then we drop down from our overlay into that distressed asphalt layer. And then we have a couple of different levels that we can use to define the asphalt layers. So the first thing you're going to do is put in the milled depth, and then you're going to put in the percent fatigue cracking. So with level 1 data, here's the drop down screen for that. And you can see that you can enter the percent fatigue cracking in directly. Now for level 3, you might not know the percent fatigue cracking exactly, but you have a general idea of where it's at. And so with this, they have a chart that is included in the manual practice, table 12-10, as you see here, the very bottom row. And that's looking at the distress that you estimate. So it's not that you went out there and defined it, but you estimate it's kind of within these ranges. And so this is your level 3. And again, the big thing about this is critical in differentiating the stiffness of that asphalt. So we're going to develop our master curve, and then based on the amount of fatigue cracking, we'll have a certain amount of damage imposed to that asphalt mixture, which will reduce the stiffness of that asphalt. How much does it reduce it is a function of the percent fatigue cracking. So either you're entering it in directly, or based on these these 5 categories, it's going to provide you with an intermediate value and define it for each one of those. Again, we'll get back to that in a few seconds. Another thing with conventional white topping in your overlay design, so joint plane concrete over asphalt, is that you must have 2 layers below your asphalt layer. And this can be important. A lot of agencies might be saying, well, we usually have a base and a sub-base layer or some type of select granular fill anyways, but in some of these thicker asphalt pavements, like they have throughout Iowa, these are full depth asphalt pavements that were constructed right on the subgrade. And so even though it's an asphalt directly on the subgrade, you will have to stick a base layer in there. And in the example, we'll talk a little bit on how that can be done. Okay, so moving right along to the project here. Again, thanks to Chris and Ben for providing us with the project information. And this is a section on US 71 in Iowa. Based on the GPS coordinates, I think it's right about in this area, someplace between Sioux Falls and Mason City, just south of 90 there. And so as you can imagine, what the climate might be up in that area. I'm sure that the winters, it gets a little bit chilly based on my experience living in Minnesota. So, colder winters and then nice sunny summers. So with this particular pavement is a 24-foot wide asphalt pavement, again, placed directly on the subgrade. And the P200, they said, was about 50%. So it's a very fine grade subgrade with a K value of 100 PSI per inch. And so just in thinking about how these are being characterized, for each design process, there's different inputs, but part of this example, I'll go through how I kind of teased out the information that we actually need for Pavement ME with the information that was needed for a different design process. So with this pavement, it was a full depth asphalt pavement, 11 inches thick. And in Iowa, what they do is they mill the profile into the asphalt so they don't have overruns of the concrete when they place the concrete afterwards. So what Chris and Ben were projecting would be a maximum of about 3 inches of AC would be removed from the surface. Now, with the design that they have, the 3-inch, upper 3 inches was a surface layer, and then the lower 8 inches was a base mix, which makes it nice too, because then you're relying on a base mix and not so much on the surface layer. for carrying the load. Because we all know the surface layer, of course, is just to cap off that, and we carry the load with the base mix. But either way, it was an 11-inch section right on top of the subgrade, and 3 inches of that was the surface layer, and 8 inches of that was the base. And then regarding the mixture characteristics for the asphalt, the P200 percent fines passing the 200 sieve was 4.3%. I apologize, I forgot my percentage there. The effective binder content was 7.5%, and then the air voids was 7%. So the distress that was exhibited based on the information they had was about 0 to 8% fatigue cracking. And then the transverse cracking was, of course, present as well, you know, as you would imagine in the cold state of Iowa in the winter there. So that was the distress prior to, you know, coming in and looking at the design. Again, I'll mention the 24-foot wide pavement section, and we'll get back to that in a few minutes as well. Okay, so the traffic, the roadway classification was a major arterial. The two-way ADT was 4,800, with 10% of those being trucks. They had a design life of 20 years, and we're assuming a 2% compound growth rate. So what's probably clicking in your mind right now is this isn't a lot of traffic. And so we'll go through the process, but you know, this gets back to the question, should we be designing this as a bonded concrete overlay, or should we be designing this as a white topping? So when the first thing we did then is look at what the properties of the overlay were going to be once they placed it. And so they use a 28-day modulus of rupture of 600 PSI. Sorry, the elastic modulus is 4 million, not 6 million. So another typo there, my apologies. The thermal coefficient of expansion was quite small, 3.8 times 10 to the negative 6 microstrain per degrees Fahrenheit. And the cement content was 550 pounds per cubic yard. Just for the sake of this design, I put 12-foot joints and also no dowels. So they were not going to have dowels in it, and we'll sort of just progress this way and continue on, and some of these other things will sort of flush out as we go. Okay, so I used a level of reliability of 85%, and again, I'll circle back onto why I did that a little bit later. But again, this is the design type is going to be an overlay over a jointed plain concrete pavement over asphalt. So back to those layer properties. Again, the subgrade underneath it was 50% fines. I used a really high erodibility, maybe is a little bit higher than what needed to be, but this is just a design example, and let's just move through it and look at where it takes us. And then also the full friction layer, as we had talked about previously. So it was a 20-year design. So for a full 240 months, we had a full friction was assumed based on what's suggested in the manual of practice. And then so for the asphalt layer properties, again, this is where we want to account for that reduction in stiffness in the asphalt layer, which is automatically done based on the amount of fatigue cracking. And I assumed, I believe that it was somewhere between, I think the fatigue cracking that was put, it was adequate. So that would be 0 to 5%. So I just put good in this area, and just interpreting what from another design procedure. So I put good and entered the 3 inches being milled right there. And then back to what we were talking about previously. So the subgrade they defined as 100 PSI per inch. And of course, we have to change that into something that the Pavement ME can use. And also we had to throw in another layer there that it would act in below the flexible layer, because again, Pavement ME requires 2 layers below the flexible layer, the subgrade and 1 additional layer. So what I did was, and again, with a K value of 100 PSI, obviously that's not great subgrade. So I selected a non-stabilized base for that 3rd layer and used the worst possible soil classification that I could, which was an A-3 under the non-stabilized base layer, and then the worst possible resilient modulus that you could use for an A-3. So that was 10,000 PSI. And then for the subgrade, that's where I tried to make things up. So for this, I used that 3rd layer, A-3, 2000 PSI, and I just made it a thin 2-inch layer. So that stiffness was only for a small thickness of a layer. And then for the subgrade, I got back to around where we should be, A-7-5, and then assigned a resilient modulus of a 7,000. Now, again, I'm doing this with the intent of trying to make that K value as close to 100 PSI per inch as possible, because if you remember when we talked about how Pavement ME designs, it's going to couple that concrete layer and the asphalt layer together, make that an equivalent slab. And then all layers beneath it, it's going to create an equivalent stiffness or a K value based on the resilient moduli. So I want to try to play with these layer stiffnesses to see if I can get an approximate 100 PSI per inch K value. Now, how do I find out if I was successful in doing that? Well, if I can get this to progress forward, what I did was go into the supplementary files that are created by Pavement ME. And if you go into the K value outputs, as you see right here, and click on that file and open up in Notepad or something that reads a text file, it will give you the K value that it estimated throughout the year. And so you see in the spring thaw or the the recovery periods, it was a little bit below 100. From the majority of the year is pretty close to 100, and then after that, a couple of months, it's about 111, 112. And so I figured this is probably a pretty good representation of that 100 PSI. This was actually my second guess at it. So you can iterate through. The first time the resilient modulus of the subgrade was a little bit too high, so I dropped that down to 7,000 PSI and got this. So again, the idea is that depending on the information you have, you can still use Pavement ME. You just might have to interpret the results a little bit to make sure that you're modeling the section that is actually out there. All right, so moving along here, we have the layer 2, which is the flexible asphalt layer. And again, that's going to be 8 inches of asphalt because it's currently 11. And as Chris and Ben had implied, it could be up to 3 inches milled off depending on the profile. And so we entered in 8 inches. For the most part, I did use the defaults, although I did enter the air voids, which if you remember was 7% and 7.5% effective binder. The other thing too, and I looked a little bit at what they use for their super pave mix, and I think it was a 58-34. So Chris and Ben, if that's not exactly what you would use out there, my apologies. But I just did the best I could based on your online documents. Okay, so then what's the results? Well, looking in those secondary output files, that traffic generated 3 million easels. And I know easels are bad, but it gives me a number that I'm familiar with. And so at 3 million easels, even when we were designing a 5-inch concrete overlay, which again is outside the inference space of Pavement ME, it recommends not going below 6. So 12-foot joints undoweled, and as you can see, the faulting criteria was just outside where you would want it to be, but in general, the cracking was negligible, right? 0.78, so not even 1% of the slabs cracked. So what this is telling me is that a conventional design probably wouldn't be the right option. And then Chris and Ben also did a design using the 93 guide, so modeling it as a new pavement on top of an asphalt base, and they got 6 inches for that. So again, it's a little bit lower. So what Chris and Ben did was they used the BCOA, and they were using 6x6 joints, so they got 4.5 inches. I had mentioned previously that it was a 24-foot wide section, so they wanted to do a 6x6 to make sure that they had the exact section length. Or width, I should say. So the 6x6 worked out well for them, and I believe they ended up going with 6 inches. So that doesn't get us where we want to be with the conventional pavement. So I just jacked up the traffic to get us to the point where a 6-inch overlay, designed exactly as we had talked about before. The only thing I did was, again, jack the traffic up. So now instead of 3 million, we have 30 million. And we had about 3% cracking at that point. And I just wanted you to focus on the cracking, because this is all about the cracking at this point. What I want to do is look at how these different, distress in the pavement prior to placing the overlay influences your overlay thickness. So again, before we were at good, but now I'm going to push that down to fair. So saying 15 to 35%, and then looking at the percent cracking. And I went, as you saw, from 13 to 31. So just by moving that down, it was pretty significant. And then going down a little bit more, you're going from 13 to 93. I didn't go down any further because, at that point, you're way outside the boundaries. And what I did, though, is go up then. So then I said, okay, well, instead of the 5, what is it if I say it's really in excellent condition, and then how would that affect the stiffness? So then I'm at 3. So I went from 13 at fair, or at good, 13 from good, and then I go to excellent, and then I got 3. So it is pretty sensitive to the distress that you put in there. So then, of course, the next question that came to my mind was, well, what if I did design this as a new pavement? And remember, the new pavement is the same in the sense that it's treating the structural, the structural response calculations, the calculations of the stresses and strains and all of the deflections, all of that, it's modeling it the exact same way. The only thing that is really changing per se is the stiffness of that asphalt. So if you had a pristine asphalt, then how would that look at it? So here I do a new design with a concrete pavement, a jointed plane concrete pavement on top of an asphalt base. And I still use the 12-foot joints in undowel. If I threw in a dowel, of course, that would disappear. So I'm not really, I'm not really concerned about that. And also I use the most erodible layer, and your faulting is extremely sensitive to the erodibility of that layer. So I'm not too concerned about that. But then when I do the 6-inch overlay with the new concrete, I go from 13 to about 2% fatigue cracking. So even if you have an asphalt in excellent condition, you do get some reduction in stiffness, and it's still not as much as it would be if you had a concrete overlay on top of asphalt. So here we're going, this again was excellent condition, 3, and then a new pavement, say 2. So, are they that different? No, they shouldn't be either. So to me, that makes a good check on how the pavement ME is working, and the consistency, and gives you additional confidence in the ability of pavement ME to predict performance, or at least it did me. So that's all that I had, Kurt. I think I'm about 5 minutes early, but I tend to talk a little quickly. So we probably have time for questions, right?
We do. Thank you, Julie, and very good information. And I think also is important for everybody to kind of get a better idea of how to proceed with some of these PCC overlay designs and what particular strategies you use. We did have a few questions, so I'll go ahead and crank those up here. Let's go back to the first one. Does new AC that is less than 3 months old have the same bond and frictional properties as a year or two old AC?
Does a new asphalt have the same bond or friction characteristics as a pavement that's a year or two old?
Yes.
There's been some research on that. You know, I think that, of course, as it oxidizes and, you know, you can increase or enhance the bond. I think also, you know, if you're milling it, then that makes a big difference as well in the texture that results after you're milling. But then again, the question I would ask is how much bond do you need, especially if it's a conventional white topping? You know, you're relying on friction in that instance and not bond.
Very good. And I think I might have missed one. So there was a question, could you send a complete family tree of decisions for white topping? I know that this webinar is being recorded, but I kept seeing that slides change and hide parts of the tree. I think we could probably provide that information, right, Julie?
Yeah, absolutely. And my apologies if I went through that a little too quickly.
All right. For the US 71 project, the K value of 100 PCI seems high. Is that corrected or uncorrected K value?
So I got the K value from Chris and Ben, and to me that doesn't seem high at all. I mean, if you look at the values that were used to back out what that K value would be equivalent to, I mean, you're pretty much looking at a subgrade of 7,000 PSI, which is not very good at all. So, you know, I did have that 2 inches of 10 million, which isn't, you know, spectacular, but it's still only 2 inches. So predominantly what's making up that stiffness is a 7,000 PSI subgrade. So I would not consider that a high K value at all. But where did I get the value? I got it from Chris and Ben. So I'm not sure of the source, but to me it made sense.
Yeah, I kind of thought the same thing. It may be a frame of reference from where the person is speaking from. What is your recommendation to design a concrete overlay on asphalt when the thickness of the asphalt is less than 3 inches or the existing asphalt is not in good condition?
If the thickness of the asphalt is less than 3 inches, then I would use an unbonded overlay design and, you know, proceed that way. The next webinar, we're supposed to include an unbonded overlay design. So we will be going over that. Again, we were going to do it in this seminar, but Jennifer and Tom in the team thought that, you know, it was a little lengthy to include it in with this, even as quickly as I speak. So the next webinar should have this, or I guess the next meeting. But if it's a white topping and the asphalt isn't in great condition, it depends on what you're demanding of that asphalt. So I don't think there's really one answer for that. You know, if it's not in great condition and you can do some minor fixes to get it in decent condition, then you might consider a bonded. If it's not in great condition, but it has stability, then maybe you want to consider more of a conventional white topping. And this is where I think the design tools will be helpful, because you saw how that it looked at and accounted for the effects of that distress in that layer. And it is pretty sensitive. Is it really that sensitive out in the field? I don't know. You know, I'm guessing in some areas, depending on where you are on that curve, it is, and then some areas maybe not as much. But I do like the fact that you can account for it, and as long as you have stability there, meaning that you have some distressed asphalt, but what's under it is stable and it's not pumping and moving around, then I think you're okay.
Yeah, I think you're right with that. And I think some agencies would also see it as kind of a risk factor. What are they willing to risk there? I mean, I know some agencies would say, well, let's just, if it's in that bad a shape, let's take it off completely and then put a new, 1-inch inner layer down and do the unbonded concrete overlay on top of that. So good
Yeah,
points.
you're right. The thing too, though, is the same thing with unbonded. You want a stable layer underneath it, so you can cover some things up that won't reflect through. But in general, if you want to make it stable, the other thing is that, you know, when you look at it from a sustainability aspect, and safer for engineers always tends to be better, but then again, do we have the money to over design everything, or should we be trying to just meet our design expectations? And because that's what our life cycle cost analysis is based on. So I know that's sort of outside a little bit, Kelly, but I guess over designing is probably just as bad as under designing when you're making your decisions based on life cycle cost.
Very good points, Julie. Another question, instead of PMED, you can also use AASHTO chart to estimate K value. However, I don't think 2-inch layer option is available. I'm not quite sure where that one's going. Do you have a thought on that, Julie?
Oh, yeah, I guess that is an interesting point. So what they're saying is that the AASHTO 93 design guide allows you the ability to convert from resilient modulus to K value. So instead of iteratively doing it through Pavement ME, I could have thrown the values in the AASHTO 93 guide and then just kept adjusting the stiffness of the two layers to get a composite K value. So the sub base and the subgrade you combine to get a composite K value, right? So maybe that's what they're saying, that it would be one way to iterate through and get a composite K value. You also have the PCC design procedure, but then of course it's not including all the layers that you can with the AASHTO 93 guide.
Yeah, that's a good point. And it looks, I mean, based on that, it sounds like, AASHTO 93 may live for many, many years. Lots of good information still in there.
Well, the one thing I would caution about, though, is that those equivalencies are probably different. So the nice thing about using Pavement ME is that, if you put those values in that you just in the 93 guide, if you use the same resilient modulus in thicknesses for each layers, you might come out with a different K value than you would for the Pavement ME design. So at least in the Pavement ME design, you're getting the K value you want, but I guess I won't even go down the rabbit hole of what the K value means and where you got it from and what you really should be relating it to. But with the 93 guide, you will get much stiffer K values, I imagine, than you would in Pavement ME. They get pretty high in the 93 guide.
Sure. Thank you, Julie. Another question, what do you recommend for the existing pavement widened in the past from 18 foot to 20 or 24 foot when we consider thin concrete overlay 4 to 6 inches?
Yeah, so Chris and Ben can probably answer that question a lot better than I can, because they've been trying to do that for years. So I guess I guess I would kind of, I don't have good guidance on that. I know that they do discuss that in the overlay design guide that the CP Tech Center puts out, and they have some great information on the construction of these overlays. So, but I also, I'm not sure too many states have more experience than Iowa. So,
Yeah. Well, that sounds like something we can tackle a little bit more after the webinar. Why not take into account the bond between the asphalt, either original or milled surface, and white topping and model that? It may contribute to longer performance life.
well, I think that essentially it does do that. And that's why the manual of practice requires that you have full friction. And, you know, the way that they're modeling it within Pavement ME, they're modeling it as one slab. So they're assuming that that concrete and asphalt are acting as one slab. And that's why it requires such a high reduction in stiffness when you're doing a bonded overlay where it's assuming the thinner short joint slabs. If you remember that short joint slab, they assume 65% fatigue cracking. And that makes a huge reduction in your asphalt. You know, the BCOA models those two layers separately. And so it can recognize the effect of the bond a little bit better. But with the model, the structural model they're using in Pavement ME, where they're assuming that it's just one slab on top of your base and subgrade, which is, you know, your bed of springs, then it's not really modeling it as debonded. It is assuming that it's bonding all the way through. In how much bond and how much does it need to engage? You know, friction in general is probably relatively sufficient when you have slabs that are 6 inches or greater, which is what this design procedure is meant for.
And to kind of go with that comment, how do you select for bonding / no bonding in the field?
Well, with a white topping, I always assume that there's going to be bond, and I never intentionally unbond or debond it unless I'm designing an unbonded concrete overlay. And by ensuring that you have just a couple of inches, then that makes sure that you have a slip plane there and it's not acting as a composite structure. So the difference though between the conventional and the bonded concrete overlays, you can be a little bit more forgiving in the amount of distress that you have in a conventional pavement and also the quality of the asphalt. So if you know, if you have a pretty good quality asphalt and surface deformations, rutting, you're just going to mill off, that bond can be enhanced. You can get a good bond though just by making sure you have a clean pavement surface. A lot of times the milling is advantageous to maintain your existing elevations or at least reduce the amount of additional height you're getting on your pavement so you don't have to build up the shoulders. So I don't think that you ever intentionally try to get rid of the bond if you're not designing an unbonded concrete overlay. But if you are designing a conventional or a bonded concrete overlay, you're always going to want to sweep the surface and make it as clean as possible and engage it in bond as much as you can. You know, what you need or require out of that existing surface is going to be different depending on how much you're relying on it, how thin you're going to get. Does that help?
Yeah, I think that helps clarify things. Let's do one more quick one, and then we'll kind of wrap things up. Do you recommend dowels for 6-inch concrete overlay?
Well, if the design requires it to carry the level of traffic without without faulting, then they're useful. Of course, the practicality of constructing it, some states seem to be successful in doing it, and others find it more of a challenge to get the baskets pinned to the asphalt, and they're concerned about tilting. So I know some states do it and they're happy with what they get out of it, and other states are not as happy about it. But whether you need them or not, which is the number one question, is to run it through the design procedure. They had 6 inches of concrete on top of I guess it would have been started out 13, so 7 inches of asphalt out on Min Road, so the interstate, which is similar to the design that we have here, and they had 1-inch diameter dowels and then the other without dowels, and the panels were 10 by 12. So a really similar design to what we have here, and there really wasn't much faulting exhibited. So 0 with the maybe it was even a 3/4 of an inch. It was a pretty small bar. So with minimal effort, there was absolutely no faulting, and then some faulting did develop in the others, but that's interstate traffic. So for this road where you have 3 million easels throughout the life, that pavement was getting 1 million easels a year. So it was way beyond this. So if you do the design and you are going to get faulting, then you might have to put in a bar to prevent that. But a lot of it's going to depend on what you have under your asphalt and the stiffness of the structure, so the overlay and the asphalt and how they're acting together. So do the design, see if you're going to develop faulting, and now whether it's conventional, then obviously Pavement ME predicts it quite well, but there's also a faulting model that was incorporated into the BCOA ME. So let the prediction tell you which direction you should head.
Great, thank you, Julie. I think we're going to cut off the questions for now, but like I said, we will address all these questions, even the ones that we've answered during the webinar, and provide the responses to all the participants in the coming days. We're getting near the end, but I did want to have a couple more poll questions. Prashant, can we load up questions 5 and 6 only? I had a couple more beyond that, but if we can do the first 2, that would be good. So these next 2 questions are just kind of helping us look forward to our future, the 2021 user group meeting and additional training webinars. As we talked about, we'll have some more training on some of the concrete overlays in the future, and this is kind of helping us along that path to figure out how we want to set these training demonstrations up. So a very simple question. Prashant, do we have a good response rate yet?
Almost 50%. So I'm going to, yeah, we just crossed 50, so I'm going to display the results now.
Okay. All right, so we have a 67% said that they don't build bonded concrete overlays on existing concrete. 20% said they do, and 13% are unsure. And let's put the next one up there, Prashant. So now we're trying to get into, if you do build these concrete overlays, bonded concrete overlays, what are you using PMED for that purpose? Wow, a whopping 92% not designed a bonded concrete overlay on concrete using PMED. So only 8% have. All right. Well, thank you everybody for your responses on that. Can you get my slides set up here, Prashant, so I can wrap up here. Couple slides. All right. Can you see my screen?
Yes, Kelly.
Great. So just a quick wrap up. We do have some upcoming events for the Pavement ME user group. We will be having the 2021 user group meeting the week of December 12th. So December 14th through 16th is what we are planning. And it will be virtual again. I will be putting out a save the date email in the next day or two. So look forward to that. Also in the spring, we'll continue with our training webinars. We'll do number 3. We haven't set a time or date for that one yet, but we will work on that. We got to get some topics put together. And then we also have in April 2022, we'll do the implementation roadmap workshop, and that will hopefully be an in-person meeting, and we'll be convening a group for that, and hopefully put some ideas out there for getting the implementation moving forward at a faster pace. Let's see. I did want to also just, I guess, mention at the 2021 user group meeting, we will put out a survey to get some ideas for future training topics. So we have an initial list of 10 topics, and we are covering many of those, and we'll have covered most of them by the end of the 2021 year. So we will have another list, and we'll try and get, what are your interest areas? What are your high interest areas? And to kind of help us guide us along as to future training webinars and what we want to cover. So look forward to that, either a pre-meeting survey, or we might do it during the user group meeting. All right, so I guess that's all I got. And again, thank you for attending the webinar. If you got any questions regarding the topics today or anything with regard to Pavement ME, certainly give us contact us at the emails that you see here with the project team, and both with FHWA, Jen Albert, and Tom Yu, and we will try to accommodate and respond to any questions or comments you might have. So again, thank you everybody, and we look forward to seeing you all in December at the 2021 user group meeting. Thank you everybody. Take care.